All right, good morning, everyone. I'm Shyam, and I'm going to be talking to you today about the interplay of star formation and feedback in dense, compact star clusters, going along the theme of looking at star formation at smaller scales than galaxies today. So, as I alluded to in my title, I'm going to be talking about star clusters in this talk, and for people thinking about galaxies and cosmological scales, might be thinking, why should I care about star clusters? So you should care about star clusters because star clusters serve as useful interfaces or units of star formation in galaxies. And you can think of star formation in galaxies as an ensemble of forming young star clusters within the galaxy. And this perspective has actually been quite useful in understanding and interpreting the properties of star-forming galaxies in the local universe. Especially for understanding things like the long depletion time of galaxies in the local universe. So I provide an example of an understanding that has emerged out of this perspective in this slide. So think of gas in galaxies. They start collapsing locally, form a cold dense phase, and then this cold dense gas collapses to form stars, and then the young stars that form within these clumps provide feedback on the surroundings and disrupt or disperse the gas. And so a small fraction of the gas ends up in stars, and the rest of the gas is ejected through feedback, where this recycled gas can undergo the same cycle elsewhere in the galaxy. So gas in galaxies, keeps cycling between the star-forming phase and its non-star-forming phase, regulated by feedback. And a key quantity that determines the outcome of this cyclic process on galactic scales is what fraction of this gas mass ends up in stars once it reaches this point. And there's been a lot of work in the past few years trying to quantify this with numerical simulations and observations. And the consensus that has emerged in that, at least in the local universe, this can not be a few percent. So a few percent of the gas mass ends up in stars, and the rest is ejected by feedback. And this, you can see, provides a natural explanation for the long depletion time in galaxies. So think of a Lagrangian gas parcel. On average, the gas parcel has to undergo many of these cycles to end up as a star, simply because this fraction is small. So the probability of ending up as a star is small. And the stellar associations that would form in such conditions would be typically unbound stellar associations because of the weaker gravitational potential wells. But that's for the local universe. As we all heard yesterday and over the several days, high-redshift galaxies are weird, and they tend to be compact. They tend to show very concentrated star formations, such as shown by Morishita et al. So this is the star formation rate surface density. It tends to be a dex to 2 higher than local galaxies, which are these contours. Effectively, you're producing, the galaxies are effectively more compact and gas-rich. And this reflects in the properties of star clusters that form. So you only see a few of these in lensed fields. Only then can you resolve these structures. And this is what I'm showing from Angela Adamo's paper. The stellar surface densities of these lensed star clusters in high-redshift galaxies are 2 to 3 orders of magnitude higher than typical star clusters in the local universe, effectively telling you that these compact conditions produce highly dense, compact, so-called superstar clusters in these high redshifts. So a natural and interesting question to ask is, does these distinct conditions of star cluster formation into distinct outcomes of the star cluster formation process, and what implications does this have on the host galaxies, on the galaxies that host them? So this is a question that I've been trying to answer over the last couple of years, and I've been trying to do this quite in a very idealized, simple fashion by running idealized numerical simulations of clumps or of star cluster forming clumps that try to emulate these distinct conditions that you see across these redshifts. So you can initialize your clouds with surface densities typical of clouds in the local universe out to these extreme conditions that I mentioned to you about. Now, what changes, I should have mentioned this in the earlier slide, is as you go to more denser conditions, the freefall time, so the dynamical time scales become shorter. So things happen much quicker. So this becomes relevant, I will show you in later slides. The escape velocity, because the potential wells are deeper, the escape velocities are higher. So and usually it's much higher than the ionized gas sound speed. And the pressures that you would find in such systems are much higher. So why did I mention all of this is because the feedback mechanisms that operate in such conditions turn out to be different. Specifically, the radiative feedback turns out to be very important in such conditions. And so we're very careful in how we're modeling the radiative feedback. We have multiple bands, and we use the Wettam scheme that I developed in my PhD, which is, for those interested in technical details, is non-local variable Eddington tensor method. So essentially, I'm just telling you, we've been careful with how we're doing this. We don't have the resolution for individual stars, unfortunately, so we have to assume an IMF, but we play around with this, as I will show you. And we also assume a dust-to-gas ratio, which we also play with. And I'll just play the movie. So the top left is the lower surface density case. The bottom right is the higher surface density, increasing from top left to bottom right. Just qualitatively, you can see the different panels evolve very differently. They look very different. They form stars very differently. Just to clarify, these movies, the cadence of these movies for each panel is scaled to their free fall time. So although the lower panels seem to be running for longer, it's longer in their dynamical times. In absolute times, this actually is pretty short. Just to clarify that. All right. So how are things different? So the first thing that is different, which you might have heard earlier, is the efficiency of star formation. So what fraction of the gas mass ends up in stars? In the first slide, I told you in the local universe, this is about a few to 10%. And that's exactly, for clouds typical of the local universe, it comes out to be about that. But when you go to these more denser conditions, this fraction of the gas mass that ends up in stars increases significantly, effectively telling you that you need to convert a larger fraction of the gas to stars for the feedback to be strong enough to stop star formation within that clump. And I'm clearly not the first person to find this. There have been many studies that find this with very different hydro codes, very different feedback prescriptions, methodologies, and this trend with the surface density of gas is quite robust across these studies, effectively telling you that this is a real result that we're seeing, and we should think more about this. All right, so one of the things that came up in the last talk was the IMF, and one of the questions that you might wonder is, okay, when you go to these high redshift conditions, these compact conditions, the IMF could potentially be different. We will hear some of this in the next talk, and what implications does this have on this picture of this high star formation efficiencies? I mean, this question has also come up in literature in the context of UV bright galaxies. If you have a top-heavy IMF, that can increase the UV luminosity, but that also could possibly decrease the star formation efficiency. So that interplay is important. And that's exactly what we try to explore with this numerical experiment by changing the light-to-mass ratio to emulate more top-heavy IMFs, and looked at the effect on the star formation efficiency within these star cluster-forming clumps. And this is the results we find. So the takeaway results that we find is that the effect on the star formation efficiency is small to almost negligible. And this is shown here. So the two panels are two different clouds at different surface densities. This is the star formation efficiency. And as you can see, the star formation efficiency does go down as you go from top-heavy IMF, like from salpeter to about 10 times the salpeter value, so a very top-heavy IMF. But even then, even for 10 times the salpeter IMF, the star formation efficiency is about 50%. So this is relatively still a high value compared to the 10% value that you would expect in the local universe. And now that is, of course, at abundance, dust abundances that's solar neighborhood-like. If you would move to a dust abundance that's about 1% the solar neighborhood value, this shoots back up to almost 100%. And this is because the radiation pressure on dust is the primary regulatory feedback mechanism here, and you lose a lot of that when you lose a lot of the dust, effectively. All right, so one other thing that might be of interest to several people in this audience is in the context of the Lyman continuum escape fraction, and how systematic differences in the cloud properties or the cluster properties might reflect in the systematic outcomes in the Lyman continuum escape from this. And we explore this in a paper that's on arXiv today. Yes, I'm one of those annoying people who time their arXiv submissions the day of their talks. Yeah, okay. So as I mentioned earlier in my talk, the denser clouds evolve quicker. So they form stars, and once they form stars, the feedback from the stars are able to evacuate the gas surrounding the stellar populations in very quick timescales, simply because they're running in fast forward. And because of that, because they remove their gas, the surrounding gas much quicker, they're able to leak Lyman continuum photons from their host populations much earlier. And this is the reason this is relevant is if you think of the Lyman continuum emission from a stellar population, it's more or less constant for the first few million years, after which it starts to drop drastically as massive stars die, because the sources of your Lyman continuum photons are going away. So having your Lyman continuum escape earlier than this timescale it's quite conducive to Lyman continuum escape, and especially in the context of reionization. And this is precisely what we see. So if you go and count, so this is what I'm showing here is the cumulative number of Lyman continuum photons that escape these clusters. So effectively, if you go outside these clusters and it sounds like a calorie counting, you're counting how many Lyman continuum photons hit you as a function of time. This value saturates at about a few million years because, as I said, the emission rate, intrinsic emission rate drops after this time scale. But the value of this saturation is much higher for these denser clusters than it is for a local universe-like cluster. And actually, there's two factors here. One is that the intrinsic emission is higher because there's higher star formation efficiency, so you form more stars. But more importantly, it's that you have escape at earlier times, specifically earlier than this time scale. But to isolate that latter effect, what I'm showing here is the cumulative escape fraction. So what fraction of the total intrinsic Lyman continuum emission of the star cluster makes it out over its lifetime? And this has a clear trend, as I mentioned, with the surface density of the star cluster. And although this is idealized simulation, these are at the cloud scale. These are the Lyman continuum escape has to still make it out of the ISM. But one thing to take away from here, more than the absolute values here, is the trend with these properties. And what this is telling you is, this trend provides a natural explanation for why the escape fractions in local universe like galaxies would be pretty small, because star clusters that are typical of these conditions should not be escaping a large fraction of the intrinsic emission. But as you go to the more dense compact star clusters, this potentially could have implications for ionization at higher redshifts. And just to make sure that I'm not sounding crazy, I want to touch upon some things that maybe folks brought up yesterday. For instance, the sunburst Lyman continuum leaker, where you see evidence of localized Lyman continuum leakage from a region that's few tens of parsec in size, very dense stellar surface densities, upwards of 10 to the 4 solar mass per parsec square, a very young region. And you have other regions in the galaxy which are more normal, you might say, but those regions don't seem to be leaking Lyman continuum photons, and they have redder slopes, UV slopes, for instance. So this could be a prototypical example of a case where you have disproportionate Lyman continuum leakage from these dense compact star clusters. Now, an implication that you could come up with, if you could assume that you have some galaxies undergoing bursts where a large fraction of their star formation is being undergone in these dense compact star clusters, then you could have even the global scale high escape fractions, as has been possibly reported by some studies, and some massive compact galaxy analogs at lower redshifts, which is toward incredibly high escape fractions. This could be possible if you could somehow distribute your star clusters in a burst in several of these dense compact objects. So I'll leave you with this, just essentially the message that your distinct conditions lead to distinct star clusters, and these distinct star clusters properties have distinct outcomes. And I list some of these outcomes, and I'm still exploring some outcomes which I'm interested to hear your thoughts about. Things like how would the nebular emission be affected, because the H2 regions that I showed are very different for these denser conditions, and I think that should affect things like the nebular emission. So I'll leave you with that. Thank you.
Can we get some help again?
Thanks for the great talk, Shyam. So your result concerning the dependence of the escape fraction on surface density, the way I understand it is your dense clouds have very short freefall times, so the gas is either consumed or expelled over a short time scale. Mm-hmm. So then you have the whole lifetime of the massive stars left to radiate freely into the surroundings. Does that describe your result?
Yes, to zeroth order, yes.
Cool. So since this is a short time scale, one can imagine other processes happening in the galaxy may be also important for determining the escape fraction of the galaxy, like other material coming in. Is that a possibility? So should we compare the escape fractions from your simulations with those measured from galaxies?
No. No. Like I mentioned, these are very idealized, isolated cloud simulations. So as you mentioned, things going on in the galaxy would come in, and this would affect the escape fractions from the galaxy. So I wouldn't take take a one-to-one result of what I'm finding here as implying that for the galaxies. But what I would take is the trends. So one of the things that I would mention in this context is what these simulations are trying to illuminate is the physics that's conducive to Lyman continuum escape. And another factor that comes up when you have these dense compact star clusters is you have many of them forming next to each other. So they don't necessarily have to be forming at the same time. So if you have a supernova going off of another compact cluster nearby that clears gas, in that complex of a few tens of parsecs, then all you need to do is escape, Lyman continuum photons from this compact star clusters, and that makes it out to the galaxy because you're punching a hole in the galaxy from this clustered formation of stars. So you see some evidence of that in some local Lyman continuum leakers, for instance. So I think I wouldn't take a one-to-one comparison here, but rather take away the physics that conducive to Lyman continuum escape.
Makes sense. Thank you.
Okay. Another question over there.
So thank you for nice talk. So I'm interested in higher electron density, very similar to the JWST observation. But so in your simulation, gas is continuously outflowing, and so that high electron density. So how long does it continue, or so during more than a million years, or only the initial phase?
Right. Okay. So you're asking how long does these high electron density, how long does the space of high electron densities last?
Yeah. Yes.
It's an interesting question. So it depends on the cloud conditions. So for the densest clouds, I actually find that I'm unable to get rid of this. So even though the escape fraction is very high at late times, I was talking about this with some people here, there are dense clumps or dense filamentary clumps that remain that are sort of in a quasi-stable scenario where it's not being driven out by the feedback, nor is it collapsing onto the star cluster or forming stars. So they're lying around, and they have the edges of those filaments are being photoionized, and the electron densities are actually highest at those recombination fronts. So you can clearly see, and those structures remain. I can't get rid of them. I've run these for several million CPU hours, so and I just can't seem to get rid of them. So this could be a persistent phenomenon.
Okay, then I ask a question. So how difficult is it actually to get the timing right for the feedback and when actually the ionizing photons are produced?
Sorry, could you repeat that?
How difficult is it actually to get the timing exact right for the feedback to actually clear the channel, and this being a time where there are actually still massive stars that produce the ionizing radiation?
Right. So this is only possible. So like I said, the timescales. If you want to escape Lyman continuum photons very early, you need to do so through feedback mechanisms that don't rely on supernovae. So by the time supernovae go off, your Lyman continuum emission starts to drop. So if you need to escape Lyman continuum photons early, you need things like radiative feedback or winds. And what I'm trying to show here is that's a possibility if you can have these very dense compact conditions. So a few things matter here. Things like the dust abundance seems to matter. If you have lower dust abundance, you would think that that's conducive to Lyman continuum leakage, which it is because you have less obscuration. But you also have less effective feedback because the radiation pressure on dust is reduced. So there's that interplay there, which is actually why I see, this is at different dust abundances, and these two competing effects actually lead to a very relatively weak dependence on the dust abundance. So yeah, there's details on that, but.
Can Mike please come forward? Thank you again.
Thank you.